Alright guys, moving on to Unit 3. We'll start with Lesson 3.1.1. This is the introduction, so make sure you listen to this part and then we'll go through examples together. In an equation with one variable, the solution will be the value for the variable that makes the statement true. For example, if 1 is the solution to this equation, x equals 1, the only number you can plug in here to make that true is 1. Okay? I know this is common sense and all that kind of stuff. 2 is the solution to the equation for 2 to the x power. That's the x right there. Okay, equals 4. In other words, 2 squared is the only thing that you can plug in for x to make it equal 4, to make that a true statement. If an equation has 2 variables, x and y, the coordinate point, x, y, that makes the statement equation true is the solution, right? The trick, though, is, so example, 1, 2 is the solution to the equation y equals 2x, because the statement 2 equals 2 is true. In other words, if you plug in 1 for x and 2 for y, you get a true statement. Okay? 1, 3 is not, because when you plug it in, you get 3, 2. We've had this conversation before. This should be reviewed. All right? The pair of values, x and y, are called ordered pairs. And the set of all ordered pairs that satisfy the equation is called the solution set. Okay, we'll talk about more today with graphing solution sets. Graphing all the possible ordered pairs that satisfy an equation of some kind. Okay? So far we focused on linear, but we're going to talk about other types too. So, each ordered pair in a solution set represents a point in the coordinate plane. When we apply these points, we get a curve. A curve is a graphical representation of the solution set of an equation. In the special case of a linear equation, that curve is going to be a straight line. Okay? A linear equation is an equation that can be written in the form ax plus by equals c. That'd be standard form, where a, b, and c are rational numbers. And it can also be written in y equals mx plus b, which is what y'all are more familiar with, which is the slope-intercept form. Right? M is the slope, b is the y-intercept. Okay? Alright, so it is important to understand that the solution set for most equations is infinite. In other words, there are thousands, millions, infinite number of possibilities that will make it true. It's impossible to plot all of them. There are several reasons that the solution set is infinite. One is that there's always a number between any two numbers, right, that will make there be a y value that is true. In other words, there's an infinite number of points that can satisfy the equation. When we graph that solution set, we're going to plot several points and connect them with your appropriate curve. Y'all are used to graphing. This is review. Again, the first lesson in the unit is usually some type of review. So, the curve that connects the points is the infinite solution set. That's probably the thing that we're not comfortable with. It's calling it a solution set. The terminology, which is something we've got to be pretty good at. Alright, so let's take a look at the example here. I think you'll find that once you get the example, this is really, really pretty easy, straightforward. Graph the solution set for the linear equation negative 3x plus y equals negative 2. Now, we've talked about how to use intercepts to find your x and y intercept and graph that way. Or what y'all are more comfortable with, for the most part, is putting it in slope-intercept form. So that's what I'm going to do. So to do that, you would start by adding 3x. Okay? Understanding that these are not like terms on the right side, so I can't combine them, but what I can do is rewrite it with my x term first, so I get 3x minus 2. Then I want to graph that, okay? So, y equals 3x minus 2, and I'm going to draw me a graph here. And this one should definitely be in all 4 quadrants, okay? Because it is possible to have negatives. We're not dealing with some kind of word problem here that prevents that. All right, so at negative 2, we have our y-intercept, and our slope is 3 over 1, right? So up 3, 1, 2, 3 over 1. All right, I think most of you will be happy with this. It's pretty easy, pretty straightforward. Now, remember, if it's 3 over 1, it can also be negative 3 over negative 1. Okay, some of us have been kind of messing that up on some things. Remember, a negative divided by negative is positive. Why is that beneficial? Because that tells you instead of just going up and right, you can also go down and left. Right? So we can also go down 1, 2, 3, left without changing the value of the equation. Right? So you draw your line. And to show that it's infinite, that it keeps going, right, you have your arrows on the end. Okay? All right, example 2. Graph the solution set for y equals 3 to the x power. Now, this is a little bit easier in terms of the fact we don't have to move anything around, but it's a little bit trickier because it's not linear. Okay? So what I would like us to do is think about some possible solutions to this. So let's start by setting up a t-chart, and I'm going to put 0 kind of here in the middle. We're going to see what happens as we go on either side of that. All right, so first off, 3 to the 0 power. If you remember our power rules, anything to the 0 power is 1. So 0 is 1. Okay? And then 3 to the first power just means 3. 3 to the second power means 3 times 3. So that would be 9. If I wanted to keep going, 3 to the third would be 27 because it's 3 times 3 times 3. Okay? Now, so let's write those out. So 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. 3 to the third is 27. You should see a pattern here that we're multiplying by 3 each time. Okay, I think everybody's pretty familiar with that and fine with that. Now, if we go the other way, what if we go to -1? Well, that means we're doing the pattern backwards, right? So going backwards, we're actually going 27 to 9 and we divide it by 3. Divided by 3 again, divided by 3. So if I take 1 and divide it by 3, I get 1/3. Okay? And then the same thing would happen if I did the -2. I would divide by that by 3. So 1/3 divided by 3 is 1/9. So this is what we're graphing. Okay? So how's that graph going to look? All right. So we had y equals 3 to the x. We had x and y, which was -2, -1, 0, 1, 2, 3. And we had 1/9, 1/3, 1, 3, 9, and then 27. All right, so I start graphing that. 0, 1. 1, 3. So right one up, 1, 2, 3. And then 2, 9. All right, and go higher. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, kind of looks linear right there. Maybe you can already tell it's not quite. And if you were to keep going out to 327, it's going to be way off the top of my graph. So I can't really do that. So let's look at the other side now. -1, so left 1, 1/3. How do you graph 1/3? Well, it's somewhere between a half and 0. So we just want to get it fairly close, as close as we can. Okay, it's a little closer to the half than it is to 0. And then 1/9, that's even closer to 0. So, but it's still not quite 0. And if we were to keep this pattern going, we'd have 1/27, 1/81. We're getting extremely close to 0, but we always seem to have a fraction with a numerator of 1 and a denominator that's really getting really big, really fast. So it doesn't ever actually cross the x-axis. It just keeps getting closer and closer to 0. So we show that by drawing a line just right along the edge of the x-axis, forever and ever. Okay? And on the other side, it increases and it keeps moving to the right. It doesn't stop. It keeps moving to the right, but it starts to go up really, really fast. Okay? This is the graph of an exponential function. So this is exponential. So we've done a linear example and an exponential example, and now we're going to do a word problem example in the next video.